Lesson: Reinforcement learning, concepts and use cases. Reinforcement learning stands as one of the most dynamic and promising paradigms in the field of machine learning, characterized by its unique approach to training models through trial and error interactions with an environment. Unlike supervised learning, which relies on labeled data, and unsupervised learning, which focuses on identifying patterns, RL is concerned with how agents ought to take actions in an environment to maximize cumulative reward. This approach has been successfully applied in various domains, from autonomous vehicles and robotics to finance and healthcare, demonstrating its versatility and effectiveness. At the core of reinforcement learning is the concept of an agent interacting with an environment. The agent's objective is to learn a policy that dictates the best action to take in each state to maximize the expected reward over time. This learning process is facilitated by rewards and penalties that guide the agent's decisions, akin to how living organisms adapt behaviors to achieve desired outcomes. The Markov decision process is often used as the mathematical framework to model these interactions, defined by a set of states, a set of actions, transition probabilities, and reward functions. One of the most notable frameworks for implementing reinforcement learning is OpenAI GYM, an open-source toolkit that provides a wide variety of environments for testing and developing RL algorithms. GYM's environments range from simple tasks like cart pole balancing to complex video games and robotic simulations. This flexibility makes it an invaluable tool for experimenting with different algorithms and honing skills in RL. The learning process in RL can be broadly categorized into model-free and model-based methods. Model-free methods, such as Q-learning and policy gradient methods, do not require a model of the environment. Q-learning, a type of temporal difference learning, is a value-based method where the agent learns an action value function that estimates the expected utility of taking a given action in a given state and following a particular policy thereafter. Deep Q networks have further extended Q-learning by integrating deep learning, allowing the agent to handle high-dimensional state spaces, such as those found in image data. Policy gradient methods, on the other hand, directly optimize the policy by adjusting its parameters in the direction that maximizes expected rewards. These methods are particularly useful in continuous action spaces and have led to the development of algorithms like proximal policy optimization and trust region policy optimization, which have shown remarkable success in various applications. Model-based methods involve building a model of the environment's dynamics, which the agent uses to simulate outcomes and plan actions. These methods can be more sample efficient as they allow the agent to simulate many interactions with the environment without actually executing them. However, building an accurate model can be challenging, particularly in complex or stochastic environments. Reinforcement learning's ability to learn from interaction and adapt to changing conditions makes it particularly well suited for real-world applications. In autonomous driving, for example, RL algorithms can be trained to make split-second decisions based on a continuous stream of data from the vehicle's sensors. Waymo and Tesla are among the companies leveraging RL to improve the performance and safety of their self-driving cars, utilizing simulations to train their algorithms under a wide range of scenarios without the risk and cost of real-world testing. In the realm of finance, reinforcement learning is used to develop trading algorithms that adapt to market conditions and optimize investment strategies. By modeling the stock market as an RL problem, agents can be trained to identify and exploit patterns in stock prices, potentially yielding significant returns. However, this application also highlights one of the challenges of RL: the need for a robust exploration-exploitation strategy to balance the pursuit of known profitable actions with the need to explore new, potentially better options. Healthcare is another domain where RL is making an impact, particularly in personalized medicine and treatment planning. By modeling patient responses as an RL problem, agents can be trained to recommend treatment plans that maximize patient outcomes. This approach is especially valuable in chronic disease management, where treatment responses can vary significantly between individuals, and optimal strategies need to be tailored to each patient's unique circumstances. ARP, the practical implementation of reinforcement learning, requires not only a solid understanding of its theoretical foundations, but also proficiency with the tools and frameworks that facilitate its application. TensorFlow and PyTorch are two popular frameworks that provide extensive support for building and training RL models. TensorFlow Agents is a library specifically designed for RL within the TensorFlow ecosystem, offering a suite of tools for developing and testing RL algorithms. Similarly, PyTorch provides libraries like Stable Baselines 3, which offer pre-implemented RL algorithms that can be easily integrated into custom applications. To effectively apply reinforcement learning in a professional setting, it is crucial to follow a structured approach. This typically begins with defining the problem and carefully modeling the environment, including states, actions, and rewards. The choice of algorithm is then guided by the problem's characteristics, such as whether the state and action spaces are discrete or continuous. Experimentation and tuning are essential components of the process, requiring iterative testing and refinement to achieve optimal performance. Real-world RL applications also demand attention to ethical considerations and the potential consequences of deploying autonomous agents. Ensuring that the learned policies adhere to ethical guidelines and do not inadvertently cause harm is a critical aspect of responsible AI development. This is particularly important in applications like autonomous vehicles and healthcare, where the stakes are high and the margin for error is minimal. In conclusion, reinforcement learning represents a powerful and flexible approach to machine learning that can be applied across a wide range of domains. By leveraging frameworks like OpenAI Gym, TensorFlow, and PyTorch, professionals can develop and deploy RL models that learn from interaction and continually adapt to their environments. Whether in autonomous driving, finance, or healthcare, RL offers the potential to solve complex problems and drive innovation. However, realizing this potential requires a deep understanding of RL concepts, careful implementation, and a commitment to ethical considerations. As the field continues to evolve, staying abreast of the latest developments and best practices will be essential for anyone seeking to harness the full power of reinforcement learning.